Welcome to MEM12003 Perform Precision Measurements. This lecture is a supplement to your student workbook and other resources made available to you. This lecture requires a basic understanding of Pythagoras' theorem and basic trigonometric functions like tangent, sine and cosine. If you're not familiar with these mathematical tools, stop the video now and review the Triangles in Engineering lecture available from Moodle. Student resources. If you haven't yet done so, download and read the student workbook, as it will assist you in completing the online quiz and practical activities. You will find similar examples and more detailed explanations of topics discussed in this lecture in the Fitting and Machining Trade textbook. YouTube is a great resource for technical information and how to do things. Cutting Edge Engineering is an example. Pause the video now so you can take a screenshot or record the YouTube address. Links described in this lecture are also available from Moodle. Don't forget to check Moodle regularly for updates and the latest information and resources for your subject. Moodle or Moodle is available on your favorite mobile device. You can download the app for Android, Apple and Windows machines. LibreOffice is the recommended alternate desktop publishing program if Microsoft Office or any other program is not available on your computer. It's free and available on all major operating systems. If you can't download anything on your computer, if you've got an internet connection and a Google account, you've got access to Google Docs. You'll be able to create spreadsheets, documents and slides, and you also get 15 gigabytes of free online storage. Of course, you need an internet connection for this to work. All the documents referenced in this lecture are available from pConnect, and of course, they're all mirrored on Moodle. All the parts and accessories discussed in these lectures can be referenced from the PerTech catalogues. Before we do anything, remember the work smart method: think, plan, do, review. You will probably remember from first year we discussed the various types of measurement tools that we can use in the workshop. Now we're going to look at more sophisticated and precise measurement methods, especially where direct measurements are not possible. Today's lecture topics. Topic number 1, setting and measuring angles. Topic number 2, precision blocks, pins and polygons. Topic number 3, dividing and indexing heads. Topic number 4, hardness testing. Topic number 5, surface finishes. Topic number 1, setting and measuring angles. Let's look at the sine bar and similar related devices. A sine bar is a device used to measure and set angles. It consists of a hardened ground body with 2 precision ground cylinders, one at each end. If you pivot the bar from one end and lift it, the center distance between the rollers never changes. When the sine bar is laid flat on a machine bed or surface plate, the center of the rollers is parallel to the top of the bar. Sine bars come in various standard lengths and accuracies. Irrespective of the sine bar angle, the distance between the rollers always stays the same. It is important to remember when using a sine bar and performing any calculations, the distance between the rollers is always the hypotenuse when we're doing trigonometry calculations. If you remember in our Triangles in Engineering lecture, or if you're already familiar with Pythagoras and trigonometry, the hypotenuse is always directly opposite the 90-degree corner or angle. We can see the configuration here. Even if we place the triangle on the surface plate or the machine bed, the angle and the distances still stay the same. Here we can see a typical sine bar application. I need to set up a workpiece at a 30-degree angle on my milling machine. How high do I need to raise one end of the sine bar? Which trigonometric function do I use? Well, the name of the tool should give it away. It's a sine bar, so we'll be using sine. Let's check this. The reference angle is 30 degrees. The side opposite the reference angle is L. And the other side is the hypotenuse, which is 100. Sine equals opposite over hypotenuse, or opposite divided by the hypotenuse. Therefore, sine 30 degrees equals L divided by 100. To solve this equation, we need to get L on its own to make it the subject of the equation. If we multiply both sides of the equal sign by 100, the hundredths on the right hand side cancel each other out, leaving L by itself on the right hand side. Therefore, L equals sine 30 degrees times 100. Sine 30 times 100 in my calculator equals 50. I will need to position the left-hand side of the sine bar up 50 millimeters to get my 30-degree angle. Here we use slip gauges. We discussed slip gauges and gauge blocks in year 1. Here's another application for using these precision blocks. Using a combination of slip gauges, we create a stack that add up to 50 millimeters, and we put it underneath the left-hand roller. Sometimes we use sine bars to measure angles. In this case, I've got a stack of slip gauges that adds up to 68.567 millimeters. What angle am I measuring? In this case, we're looking for the angle, so it's still the reference angle. We'll use the Greek letter theta for the angle. We have an opposite and a hypotenuse, so it's sine. Let's populate our formula. Sine theta equals opposite, which is 68.567, which is our stack of slip gauges, divided by the hypotenuse, because it's a 100 millimeter sine bar. On my calculator, if I'm looking for the angle, it's shift sine 0.68567 equals 43.288 degrees. Here on image 1, we can see the angle being set for a taper turning attachment on a lathe. On image 2, we can see a setup for an angle milling operation. Many work holding devices and measuring devices utilize the same principle as a sine bar. For example, we have a sine vise and a compound sine vise. Section 2, precision blocks, pins and polygons. As discussed in year 1, gauge blocks come in various grades or tolerances, from workshop to calibration grade. Calibration grades are sometimes manufactured from ceramics and carbides, giving them better wear and thermal stability properties than steel. Precision pins and rollers are available in various grades and size ranges. Precision balls and angle blocks are also available in various grades and ranges. Let's look at a common measurement challenge that we'll face in a workshop. We have a machined V-groove that we need to measure the exact depth, angle and width. In this example, we will use a precision pin or roller or ball to measure the depth of an angled groove. In this example, I need to calculate what X should be, and I'll use a depth gauge or a height gauge to measure from the top of the V block to the top of the ball or cylinder. The following example is for demonstration purposes only and not expected to memorize all the steps, as these skills will come by practice and repetition. This is going to take a few steps. So the first thing I need to do is work out the distance from the center of the ball to the bottom of the V groove. As we can see, where the diameter of the ball touches the side of the V groove, it creates a 90-degree angle. So we can create a right angle triangle. In this case, we're looking for C, which is the hypotenuse of the triangle. We have a reference angle on opposite side and a hypotenuse. So sine equals opposite over hypotenuse. So we'll be using sine. Our reference angle is 45 degrees because it cuts the 90-degree corner in half. Let's populate our formula. Sine 45 equals opposite over hypotenuse. So sine 45 equals 12.5 over C. We need to get C out on its own or make it the subject of the equation. So first thing we'll do is we'll multiply both sides by C. Therefore, both C's on the right hand side will cancel each other out. Now we have sine 45 degrees times C equals 12.5. Let's divide both sides of the equal sign by 45 degrees or sine 45 degrees. The sine 45 degrees both cancel out on the left hand side, leaving C on its own and the subject of the equation. Therefore, C equals 12.5 divided by sine 45 degrees. So 12.5 divided by sine 45 degrees equals 17.667. Before we continue, you might remember we talked about special triangles in engineering. Here we have an isosceles triangle. We have both angles of 45, therefore both sides, A and A, are the same. So to solve the hypotenuse, all we had to do was A times the square root of 2. So 12.5 times the square root of 2 equals 17.667. Remember, if in doubt, use Pythagoras or trig. Okay, remember, X distance is from the top of the V block to the top of the ball. So first thing we'll do, let's work out, we'll call it Y, which is the hypotenuse plus the radius of the ball. That will give us the distance from the bottom of the groove to the top of the ball. So what we have here is C, which is the hypotenuse, 17.667 of the triangle we created from the center of the ball to the bottom of the groove, plus the radius will give us the distance from the bottom of the groove to the top of the ball. So Y equals 30.117. As you can see, we're using triangles to derive information. Let's think about this. So I've got the distance from the bottom of the groove to the top of the ball. If I subtract the distance from the bottom of the groove to the top of the V block, I'll get my X distance. In other words, X equals Y minus our Z value, which is the distance from the bottom of the groove to the top of the V block. Let's calculate Z. We have a reference angle. We have a length adjacent to the reference angle, and we're looking for the length opposite the reference angle. So opposite over adjacent equals tan. Tan equals opposite over adjacent. Therefore, tan 45 degrees equals Z, which is the length we're looking for, divided by 25. There's our special triangle again, but we're going to use tan in this example. Tan equals opposite over adjacent. Therefore, tan 45 degrees equals Z divided by 25. I need to get Z on its own to solve the equation. Let's multiply both sides by 25. So that's both sides of the equal sign by 25. So the 25s on the right hand side cancel each other out. Z is now on its own, so tan 45 degrees times 25 equals Z. And I type that into my calculator, and Z equals 25. If you remember, the formula we created was X equals Y minus Z. Now that our formula is populated, it's now called an equation. So X equals 30.177, which is the Y distance, minus 25, which is the Z distance we just calculated. So X equals 5.177. Now that I have a master reference, I can start measuring my V grooves with my 25mm ball or roller and make sure that my X distance is within acceptable tolerance. And what's the tolerance for my component? Again, I referenced that from the Machinery's Handbook. Finding the angle. Using the previous example, I've measured 4.117mm for X. What's the angle now? In this example, I know what X should be. I subtracted what I measured for X and added it to the Y dimension. Now all I have to do is subtract the radius of the roller, and I have a hypotenuse. Using sine, I can work out the angle A, double it, and I have the included angle theta. This can be confusing, as the smaller X dimension means that the groove is actually deeper. Don't be afraid to use other tools to check your calculations. Here I've used my CAD skills from Year 2 to draw and analyse the V block. If you remember, in Year 2 we talked about spreadsheets. Here we have an example of a spreadsheet that's set up to calculate the angle automatically. All I have to do is input the measured X value, and my spreadsheet formula will automatically calculate the angle. I can set up the spreadsheet to give me any information that I need off the V block. As with the previous example, we did have some information that we could use to create triangles and derive the other missing information. What if we don't have any other information? What if we just have a machine V groove and a precision ball or pin or rod? How would we go about measuring the V block successfully? Shadow graphs or projectors are commonly used for measuring difficult components. As with the example on the right, we have a screen with graticules with angles and distances, and the table has micrometer divisions for taking direct measurements of the profile of the component. Some projectors are manual with vernier or micrometer graduations on the table, and some projectors, shadowgraphs, have a onboard computer that can automate measurements like angles, squareness, distances, diameters, and so forth. This technology is relatively inexpensive, but limited to the size of the components that can be measured. For larger objects, or for objects that have internal cavities and features, coordinate measuring machines and programmable height gauges are another option. This technology is readily accessible, and the cost of this equipment has reduced considerably in recent years. Dividing and indexing heads. Rotary tables. A rotary table is a precision work positioning device used in metalworking, mainly on mills, drilling machines, boring machines, and they enable an operator to drill or cut work at exact intervals around a fixed axis. As with any machine tool accessory, rotary tables come in various sizes and configuration. Here's an example of a compound rotary table. Works the same way as a sine bar, where we put slip gauges underneath one end to set angles. The same work holding devices that you'd find on a lathe can be used on a rotary table. 3 and 4 jaw chucks, clamp kits, magnetic chucks, collet chucks, and vices. Rotary tables come in manual, semi-automatic, and fully programmable for interfacing with computer-controlled machines. Here we can see an example of a rotary table used to machine a PCD of holes, or pitch circle diameter of holes, on a mounting plate. In this example, we have 8 holes, so 360 degrees divided by 8 is the spacing of 45 degrees. Here we can see on the job setup table, hole number 1 will be 45 degrees, hole number 2 will be 90, and it increases in increments of 45 degrees until we get to 360 degrees. Obviously, if I drilled my first hole at 0 degrees, my 8th hole would be at 315 degrees. Irrespective if it's a lathe, a mill, a rotary table, remember, we always wind the handle in one direction. If we're going to change direction for whatever reason, we've missed a reading, we always go further, about half a turn, and then reverse the direction of the handle. Indexing heads, or dividing heads, are a close relative to the rotary table. This device uses indexing plates and plates with notches to rapidly position the workpiece at specific angles. Indexing head has the work holding area. As with the rotary table, 2-jaw, 3-jaw faceplates, vices, collet chucks can be mounted for work holding. We have the crank handle, sector arms, and hole plates. We'll have a look at these individual components in a few more slides. There are 3 main methods of using a indexing head. First one is direct indexing. This is a ring with holes situated directly behind the work holding device, and there's a quick release pin that can be engaged. Usually the plate is made up of 24 holes. With the 24 hole plate, for example, we could evenly space a hex or a hole pattern or gear teeth with 2, 4, 6, 8 or 12 teeth evenly around the diameter. The second method is using the differential ratio. Using the hole plates, we can do partial turns or odd-numbered spacing on the component. In this example, I want to cut a gear with 200 teeth around the outside diameter. I have a 40:1 ratio between my crank handle and the work holding device, so I have to wind the crank handle around 40 times to get my work holding device to rotate once. This is simple. My gear ratio divided by the number of increments or gear teeth in this example that I need, which is 200. Gear ratio of 40 divided by number of teeth or increments, 200. So 40 divided by 200 equals 1/5 or 1/5 of a turn. 1/5 of a turn of the crank handle. Well, how do I get a 1/5 of a turn? What I'll do is I'll pick the 15 PCD hole ring on my hole plate, and if I divide that by 5, every 3 holes is a 1/5 of a turn. I could have picked any hole ring that was evenly divided by 5. You can see in this diagram I've set the sector arms to 3 holes so I can quickly index those positions. The main nut in the middle of the locking pin arm can be adjusted to allow the alignment of different hole PCDs on the hole plates. Let's machine a hexagon or Miller hexagon on our indexing head. I have a gear ratio of 40, 6 sides or 6 indexes. So 40 divided by 6 equals 6 4/6. If I reduce that down, it's 6 2/3. So I will need 6 complete turns and 2/3 of a turn for each side of my hexagon. So I have 2/3 of a turn. Let me look on my hole plate. Do I have a PCD that's divisible by 3? Yes, I think I'm going to use the 27. There's a few others I can use, but 27 looks like the one that I'm going to use. So 2/3 of 27 is 18. So I'm going to use 18 holes of a 27 hole circle to get me my 2/3 of a turn. So I'll set my sector arms at 18 holes of the 27 hole circle ring from my starting point. The third method is the angular method. If we divide the circumference by the gear ratio, that means every wind of the crank handle will move the workpiece 9 degrees. In this case, if I wanted to rotate my workpiece 45 degrees, so it's 45 degrees divided by 9 degrees equals 5 turns of the crank handle to position my workpiece 45 degrees. Indexing takes a lot of practice, especially if you're setting up your first job. Always do a light scratch cut around all of the indexes to make sure that you haven't made a arithmetic mistake. In this example, we're going to cut a spur gear, so we can see that we're using a mandrel to hold the gear blank. The indexing will be done with a dividing head and it'll be held between centres. In the image below, we can see that the mandrel is being checked for squareness and run out. It's a 25 tooth spur gear, so our gear ratio of 40 divided by 25 teeth equals 8/5 equals 1 3/5. To get the correct tooth spacing, we'll need 1 full turn and 3/5 of a turn. I will need to choose a whole circle that can be divided by 5. 15 can be divided by 5, so I'll use a 15 whole circle on my indexing plate. 15 divided by 5 equals 3. I need 3/5, so 3 times 3 equals 9. There is a number of ways to derive the fraction. Use a system that you're comfortable with and confident with. As you can see, the dividing head has a matching tailstock. The actual center height can actually be adjusted with the tailstock. On the bottom right hand corner of the slide, we can see that the module cutter or gear tooth cutter is mounted in the vertical spindle. Section 4, hardness testing. You'll remember from year 1 that we can alter the mechanical properties of steel or carbon steel by heating it up and quenching it. This will make the steel hard, but how hard? We use hardness testers to measure the exact hardness of metals. Let's do some quick revision from year 1. Hardening makes the metal hard, tempering makes the metal tough, and annealing makes hardened metal soft. What is hardness? Hardness is a measure of resistance to deformation. In plain English, what force is required to dent or scratch a bit of metal or any other material? Therefore, the smaller the indentation given a force, the harder the material. There are many hardness testing systems and methods out there. Today we'll be looking at the 3 main ones that concern our particular industry, which is Rockwell, Vickers and Brunel. Why do we test things or objects for hardness? Well, characteristics, for example, to check the material. Is it the right material? To check the hardenability. Did we actually do any hardening when we heat treated the component? Testing to confirm that parts are within specification, and we can use it to predict the tensile strength. Functionality. We're testing to see that the component is fit for purpose. As already discussed, there are many different methods of testing for hardness. How do we know which system to choose? Well, first one, what material are we testing? What size is the component that we're measuring? How thick is it? The scale. The shape of the object. Is it irregular? Is it flat? And the repeatability of my measurement. In other words, the precision that we can obtain by taking a measurement. Will I be using a fixed machine or a portable machine? The first system we're going to look at is the Rockwell hardness testing method. This is the most used hardness testing method in our industry, and it's more accurate than other types of hardening testing methods. The Rockwell method uses an indentation method. It basically measures the depth of an indent at a certain load or force on the indenter. Here we can see 98 newtons of force are placed on the indenter, and the permanent depth of the indentation is measured. depth to force ratio gives us the hardness in Rockwell. The second hardness method is the Brunel hardness test method. The Brunel method is commonly used to test materials that have structure that is too coarse or that have a surface that's too rough to be tested using any other method. For example, castings and forgings. With the Brunel method, a predetermined force on an ultra-hard ball is exerted on the workpiece. The indenter is then backed off and removed, and the area of the indent is measured. The resulting impression created by the hard ball is measured with a specially designed Brunel microscope or optical system. The third testing method that we're looking at today is the Vickers hardness test method. Similar to the Brunel hardness testing method, an indentation is later measured using an optical system. The Vickers hardness testing method is usually used for ultra-thin materials like foils. Vickers test forces are typically below 1 kilogram. Take note that some Vickers test machines can range up to 30 kilograms or more. The Vickers system utilizes a pyramid-shaped indenter. A certain pressure is applied, then the indenter is backed off, and the indentation is then optically measured. Once again, the hardness value is a ratio between the test force and the surface area created by the indentation. Hardness testers are available as bench mounted. Hardness testers are also available as a portable unit. Hardness testers are available in electronic versions, pocket versions. We even have a hardness testing file set. Again, this is for testing hardness using the scratch method, not the indentation method. Hardness testers are available in multifunction, multi-system, and programmable. This all depends on your budget, the environment, and application, of course. There'll be occasions where you're working in one system and you're testing and measuring in another. Conversion tables come in handy. There's plenty of those available on the internet. There's always your machinery's handbook, and there's plenty of apps that you can utilize and download on your favorite mobile device. The practical activity for this unit involves you manufacturing a portable hardness tester of your own. Surface finishes, or measuring surface finishes. You'll probably remember from year one the term surface finish. We discussed measuring surface finishes. It's basically to describe the texture or the surface of a component we've just machined. Just a revision from year one, 3 things that determine surface finish: the waviness, the lay or the direction of the grooves, and the average of the surface roughness, the RA value. There's a couple of ways that we can measure surface finish or roughness: comparative, by using a comparative gauge, or a direct measurement using electronic device which runs a stylus over the surface and gives us the information we need: average surface roughness, waviness, etc. What if I don't have a surface finish gauge? How do I create these surface finishes? Even if I had a surface finish gauge, how do I set my machine to give me these surface finishes? We're going to have a look at that now. In this lecture, we'll be looking at turning. The value will be RA in micrometers. Really rough is 12.5, so if we see a 12.5 surface finish on a mechanical drawing, it basically means really rough, usually surface prepared for painting or something like that, and a really smooth, usually for bearing surfaces or mating parts. Just make a note that the surface finish relates to a particular machining operation, and we can see here the 12.5 micrometer looks very different for horizontal milling, vertical milling and turning. So be aware of your machining operation. These two formulas will come in very handy, because if I don't have a surface finish gauge, I can use these formulas to set up my machine to give me those surface finishes. The feed rate formula tells me what feed rate setting I have to use on my machine to get a particular surface finish. I can also calculate the surface finish from the feed rate, depending what information I'm looking for. Let's calculate a feed rate. So what information do I have? Well, my tool has a 0.8 millimeter radius, and my drawing specifies a 3.2 micrometer surface finish. So what do I have to set the feed rate on machine to get this surface finish? Let's populate our formula. 8 times the tip radius times the surface finish I'm looking for, divided by 1000. Remember my order of operations, so I have to do everything underneath the square root sign first before I can solve. Therefore, with a tool radius of 0.8 millimeters, and I need a 3.2 micrometer surface finish on my component, I will set my feed rate to 0.143 millimeters a rev, or the closest setting on my gearbox to that value. Here's a picture of my gearbox feed selection table, and looks like 0.14 is the closest feed to the one that I need. Let's go the other way. What will the surface finish be if I have a tool radius of 0.8 millimeters and I've set my machine at 0.05 millimeters per rev? Let's populate the formula. Now we have an equation. Don't forget our order of operations, and we end up with 0.4 micrometer surface finish. Keep in mind, depending on the radius and the feed rate, we might end up in between surface finish values on our surface finish gauge. Here we can see a shaft with multiple diameters and multiple surface finishes. If we apply our feed rate formula for each one of the diameters, we can see that we can calculate the specific feed rates that we'll need for each diameter to get the correct surface finish. Returning to my lathe feed rate chart, I've selected the settings closest to the ones that I calculated using my feed rate formulas. There are a number of similar machining operations that can result in similar surface finishes. For example, turning and milling. Online reference charts and reference materials like the Machinery's Handbook are handy for this type of information. There are a number of surface finish systems out there, RA inch and RA millimeters, which we're already familiar with from our surface finish gauge. There are some older systems out there also. Sometimes a quick comparison chart will be useful in these situations, from converting from one system to another.